We're going to work on an ALEKS problem that deals with calorimetry. In this example, a 59.7 gram sample of aluminum, which has a specific heat capacity of 0.897 joules per grams per Celsius, is put into a calorimeter that contains 100 grams of water. The temperature of the water starts off at 23 degrees Celsius. When the temperature of the water stops changing, it's 30.7 degrees Celsius. The pressure remains constant at 1 atmosphere. Calculate the initial temperature of the aluminum sample and be sure your answer is rounded to the correct number of significant digits. So in this example, a piece of metal is placed in water. The water starts off at a certain temperature, and after a while, it stops at a slightly higher temperature. So basically, a hot piece of metal was placed in the water, which allowed the water to go up in its temperature a little bit, increase its temperature. So we're going to start off with our given, but we want to remember that this problem deals with two different samples. So we're going to have to make our given a little bit more organized. We're going to use the subscript M to mean metal and the subscript W to mean water. So the mass of the metal is 59.7 grams. It has a specific heat of 0.897 joules per grams per Celsius. It was placed in 100 grams of water, and the initial temperature of the water was 23.0 degrees Celsius, and its final temperature was 30.7 degrees Celsius. Since we have the final and the initial, we can go ahead and solve for delta T, which is final temperature minus initial temperature, which equals to 7.7 degrees Celsius. We also have the specific heat of water, which is 4.184 joules per grams per Celsius. We can look that up on a table. We're asked to find the initial temperature of the metal, but we do also need the final temperature. So if the hot piece of metal was placed in water, eventually thermal equilibrium should be reached, which means that the metal and the water should have the same final temperature. So the final temperature of the metal is 30.7 degrees Celsius. We have all the given, so now we want to plug this into some equations. We know that the heat that's given off by the metal should equal to the same heat that's taken in by the water, but it's going in a different direction. So we put that negative Q there. So what this means is that the heat that is given off by the metal should equal to the same heat that's taken in by the water. One gives and one takes, and we show that mathematically by making one positive and one negative to show a different direction. We know the formula for Q. Q is just C times M times delta T. So we're going to do that on both sides, but not to forget the negative sign. And we're going to start plugging in some numbers. Delta T is just final minus initial temperature. We're going to do the same thing for the water. On the metal side, we do have the final temperature, so I can plug that in. All right, let's clean up our math here. 0.897 times 59.7 needs to be distributed into the parentheses, so we're going to go ahead and say that times by 30.7, and this equals 1.644 times 10 to the third. 0.897 times 59.7 times Ti equals 53.55 Ti. On the right, we can go ahead and multiply negative 4.184 times 100 times 7.7. In order for us to solve for this equation, we have to get our numbers on one side and our variables on another side. So the first thing I want to do is go ahead and add 53.55 Ti on both sides. This cancels it on the left side. I'm going to get my constants on the other side, so that means I'm going to have to add 3.2217 times 10 to the third on both sides. So when we add these two numbers, we get in order for us to solve for our unknown, our TI, we have to divide on both sides by the coefficient. And TI equals 90.9 degrees Celsius. However, they want our final answer in the correct number of sig figs. So take a look at our given table, and we see that the fewest sig figs that we have is 2 sig figs. So our final answer should have only 2 sig figs. So our final answer is 91 degrees Celsius. And ALEKS would prefer if you put that decimal place there to show no decimal places. Let's take a look at another example. In this example, a 55.7 gram sample of quartz, which has a specific heat capacity of 0.73 joules per grams per Celsius, is put into a calorimeter that contains 250 grams of water. The temperature of the water starts off at 25 degrees Celsius. When the temperature of the water stops changing, it's 27.4 degrees Celsius. The pressure remains constant at 1 atmosphere. Calculate the initial temperature of the quartz sample and be sure your answer is rounded to the correct number of significant digits. Again, we want to have a given table with 2 samples. We're going to have the quartz and the water, and for consistency, I'm just going to use the subscript M for metal, even though quartz is more like a mineral. So let's go ahead and do that. And it says our quartz has a specific heat capacity of 0.73 joules per grams per Celsius. It's put into 250 grams of water. The initial temperature of the water is 25 degrees Celsius. The water's temperature stops changing at 27.4 degrees Celsius, so we can go ahead and solve for the delta T, which is final temperature minus the initial temperature. We can also find the specific heat of water on a table, 4.184 joules per grams per Celsius. They're asking us to solve for the initial temperature of the quartz. If the quartz was placed in water in an insulated container, then they should reach the same final temperature. So the final temperature of the quartz is 27.4 degrees Celsius. We have all of the given, so we want to plug this into a formula. The heat of the quartz that is given off should equal to the same heat of the water that is accepted, but in a different direction, negative. So the heat of the quartz that is given off should equal to the heat taken in by the water. One gives, one takes, so one is positive, one is negative. The formula for Q is C times M times delta T on both sides. We're going to plug in our numbers. Delta T is final minus initial. I do have the final temperature of the quartz, so I'm going to plug that in. All right, I want to distribute 0.73 times 55.7 inside the parentheses times 27.4. 0.73 times 55.7 times TI. Negative 4.184 times 250 times 2.4. I'm going to give my constants on one side, my variables on another side. So I'm going to add 40.66 Ti on both sides. This cancels out. I'm going to add 2.5104 times 10 to the third on both sides. I'm going to divide by my coefficient on both sides. So Ti equals 89.1 degrees Celsius. However, our final answer needs to have the correct sig figs. Take a look at our given table. And the fewest decimal places the fewest sig figs that we used was 2.4, which is 2 sig figs. So our final answer is 89 degrees Celsius. Remember that ALEKS likes for you to put that decimal point in. Good luck and keep practicing.